In the last video, we talked about the Fourier series, and we might wonder, why would we really want to know about the Fourier series? What does it tell us? Well, first, you should recognize that it's a form of superposition, so it's a linear function, and it allows us to break nonlinear, allows us to break down nonlinear functions into an infinite linear form. Why is that important? Well, let's say that I want to analyze a sound, and the sound happens to have a shape like a pulse. Imagine this being periodic. Well, this is the worst. This is the worst waveform to study or to analyze. It's very difficult because you have these sharp edges. It's very hard to come up with functions that you can put into equations to make any kind of sense. But if I can use the Fourier transform, then I can analyze the system one wave, one cosine, one sine wave at a time, and then I can just take the results and see what the end result is. So if I have some box that I'm putting in this pulsing sound, we'll call it the black box. Then let's say I have my input signal going in, and I want to do some kind of analysis. Well, what I can do is I can run this through a theoretical box. We'll call it the Fourier Series generator. And this box would have multiple different inputs into this box, each of these inputs being the harmonic. So I'd have the first harmonic, second harmonic, third harmonic, fourth, fifth. I could do how many more harmonics that I want to do to some value n. And then I can take and look at each of the results This would be for the result or the output of the first harmonic. This would be output of the second harmonic, third harmonic, fourth harmonic, fifth harmonic, and then I would just put these into an adder and I would get my output. This is the kind of process that you can go through to solve these kind of problems and to make it easier to do an analysis. It means a lot more paperwork, but it's a lot easier than trying to analyze these pulsing signals or some kind of discontinuous signal. Now, in audio, you'll find what's called a spectrum analyzer. And it just breaks down graphically the different frequency components. Of sound. And you can use them for other things, but right now we're talking about for sound. You could use it for electrical signals or whatever you want. And this spectrum analyzer helps to identify the quality of the sound. You could say, is it a pure tone? Pure tone being a specific sine wave, in that you can basically see one sine or cosine wave and all the others disappear. And this is used quite a lot in the audio industry and even in engineering. It's a very useful tool. Now, this is what a spectrum would look like. And here we have the spectrum of different instruments. The first one's a clarinet. And you notice here at the front, this is the first harmonic. This would make this the second harmonic. And then you'd have the third, fourth, fifth, sixth. So you notice that you have this strong first harmonic, and then the harmonics start to decrease, and then at the higher frequencies the harmonics appear again. And this is not really a pure tone. You have all these other components going with it, and this is what the spectrum analyzer would help you to see. Now for a piano, you can see that it's even worse. There's a lot of overtones or a lot of harmonics that are going on for a specific note. It's not as clean as you would think it would be. But look at the violin. The violin here has a good strong first harmonic, and then all the other harmonics die away for a specific tone. So this is the purest or cleanest tone in an orchestra. So if you ever go to a concert or where they're playing in an orchestra, you will notice that the first violin plays a tone. That is the pure tone that everybody will tune their instrument to, because it is the purest. So that's the job of the first violinist, is to get everybody else in tune, and that's because he has the purest sound that everybody tunes to. As long as everybody tunes to his violin, the orchestra will sound good. So this is the idea of Fourier series and how it's useful in analyzing sounds. And it also allows us to be able to analyze noise. Now there's different kinds of noise. I'm just going to mention them. I'm not going to require you to know them. The subject of noise is a very long and rigorous subject, so we won't be able to get into it too much. But there are a couple of different types of noise that are used in audio. The first one is called white noise. And white noise is the best way to describe it. It's the sound that you hear on old televisions when they're not tuned to a channel. You know, when you had the snow on the screen and you hear that hissing sound, if you were to look at a spectrum of that sound, you would find that it's very random in amplitudes, but they're all fairly well in some average, there's some average value here in this waveform. But they're all, it's called stochastically distributed, randomly distributed around this average. Now there's also one that's called pink noise, and this noise is actually used when someone's doing a sound check in a room to see just how the quality of the sound is. And a pink noise it has a different waveform. It's stochastic, it's random, but it's increasing amplitude with frequency. So there's some slope function that gives you the average, and this noise is just stochastically going around this noise. And these amplitudes change and pulsate and move in time. And so you get the hissing sound that you associate with that kind of noise. Typically, you want to get rid of noise. Uh, White noise occurs naturally, but pink noise is usually generated. It's very difficult to get rid of noise. It's not an easy thing to do because noise can exist at all frequencies. So it's a topic that you need to know at least a little bit about what causes noise, the types of noise. But as I said, there are classes specifically dedicated to noise and what it represents and how to deal with it in systems that you analyze. So we won't get into that, but it's good for you to just know a little bit about it.